Okay, today we're going to look at rotations. You should have this out. All right. Oop, there you go. Okay. So rotations is our section. Here's your definition of a rotation. It's just a turn around a point. Okay, so for example, my flower here is turning, okay, about this point. The tennis ball, again, turning, and the TV turning on its side. Okay, this is what the letter W would look like if we turned it. So if we turned it 90 degrees, it would look like this. If we turned it 180, it would look like an M. And if we turned it 270, it would then look like a weird 3. Okay. Concept map. Okay, transformation is our general term for just any slide, turn, flip, or dilation, which we'll talk about later. But it describes a change made to an object or its position. Example, a translation or a rotation. Okay, so if I take this and make this into a concept map, transformation would be our main idea. We said right here, it describes a change made to an object. Example, translation or rotation. So common sense would then put translation and rotation here. Translation is what we talked about the other day. That's your slide, okay? And the new one for today, the rotation, is a turn. Okay? Center of rotation is the point that the rotation turns around. So it could be at the center of the object, like with a wheel. It could be on the object, like a door hinge. Or it could be off the object, like an anchor for a boat. Okay, here's some samples. So here I've got my xylophone. Here the point of rotation is off the shape, okay? Here in our Ferris wheel, it's going to be inside the shape, okay, if this were to go around. And then our book, it's going to be on the shape, okay? So it's going to be your binding of your book. Well, let's see if this works. Okay. I don't know if you can see that. I'll try and, well, can't bring it down. But you can kind of see we have the Earth spinning on its axis. So there would be another example of it being on the shape. Okay. Okay, rotational symmetry. We talked about translational symmetry the other day. Okay, rotational symmetry is if it looks the same after a rotation of less than 360 degrees. Okay, so for example, my division sign, okay, I can spin this. It doesn't look the same, doesn't look the same, doesn't look the same, doesn't look the same, but now it does. And I did a half turn to get there, okay? My plus sign, okay, here it looks the same right away at a quarter turn, also at a half turn, and a 3/4 turn. Okay, so those both have rotational symmetry. Our box here, okay, if I rotate it, here the outside's the same, but my diagonals are now going in different directions. So that is not quite rotational symmetry, but if I go to my half turn, okay, there it is, it looks like it did at the beginning. And our wheel over here, okay, this is going to have all kinds of them. All right, so we got rotational symmetry all kinds of places. All right, and let's see if this one works. Nope. All right. Okay, basketball court. To describe rotational symmetry. Okay, so when I say to describe it, that doesn't mean describe it in words. I want to use numbers, okay? So to describe rotational symmetry, you need to tell how many degrees the object must rotate in order to look the same way it did before the rotation. So if I were able to take this basketball court and rotate it, so you could on your paper, okay, we'd be able to do a half turn on it, okay? So if we had to describe the rotational symmetry that this has, we would say that it has 180 degree rotational symmetry. Okay? Rotation of 90 degrees. Okay, this is what one might look like if we're going to rotate it 90 degrees. So here's our triangle here, all right? And we're rotating it 90 degrees. If you look right in this part here, in the blue part, for example, you can see there's a 90 degree angle from C to R, all right? And then in here, from A to P, there's also a right angle in there. Okay, I'll make it just a little bit bigger. And then, of course, we've got another one in here, okay, from B to Q is another right angle. So in your head, you're kind of visualizing, all right, if I turn this whole thing 90 degrees, that's what it would look like. Okay, so down here it says, in the above example, every point of the triangle ABC is rotated by 90 degrees to get the duplicate triangle PQR. All right, so on your graph paper, this is challenging, okay? But what I'd like you to try and do is rotate this shape, and let's go 90 degrees counterclockwise. Okay, think of how a clock goes. A clock goes this way, right? Okay, so we're going to go counterclockwise. So I want it to end up, it's going to end up over here in the second quadrant. All right? So I want you to try that. Go ahead and pause and see what you come up with. All right? Now I'm going to try it. Okay, that's your answer. All right, I did that a couple ways. I kind of combined it with a couple things in my head. All right, so I said I knew it was going to end up over here in the first quadrant. Okay, I knew it had to be just one away from the axes. So here it's one away from the x-axis, so it's going to be one away from the y-axis. I then looked at my ordered pairs. Okay, there is a little bit of a pattern here. The original point was at 1, 2, 3, 4, 5, 1. So that means this one's going to be at negative 1, 5. Okay, this one's at 7, 1, so it's going to be negative 1, 7. Okay, so that would be a 90-degree rotation counterclockwise. All right, I'd like you to use that information, and I'd like you to try and do 90 degrees clockwise. All right, so 90 degrees clockwise. And then I want you to try 180 degrees. Now, I'm not going to give a direction on that because it's not going to matter if I go clockwise or counterclockwise. All right? So, call me over when you get those two, and we'll see how you do. All right? And then what we're going to do here is we're going to see what kind of rotational symmetry this has, and then we're going to describe it. So, in other words, if I were to rotate this, I could rotate it 1, 2, 3, 4, and I'd be back up to where I started from. So when I figure out what kind of rotational symmetry this is, I take 360, which is a full circle, and divide it by 4, because it was 1, 2, 3, 4 turns to get all the way around. Well, 360 divided by 4 is 90, okay? So we would say, yes, this has rotational symmetry at 90, and then the next quarter turn would be 180, and then the next quarter turn would be 270. We don't say 360 because everything has 360, all right? So we only list up to 360, not including 360. All right, on this one, okay, it would just be a half turn, okay? Half turn, or in other words, if it's 2 turns to get all the way around, 360 divided by 2 is 180. So we would say this one has rotational symmetry, yes, at 180 degrees. Okay? All right, this one has 1, 2, 3, 4, 5, 6 sides. So on this one, I'm going to take 360 divided by 6. Obviously, that's going to be 60. Okay, so this is going to be yes at 60, and then I'm just going to list every 60 degrees. So 120, 180, 240, 300, and then again, we don't list 360. One way to check yourself, we divided by 6, we should have 1, 2, 3, 4, 5 answers. We should have one less than how many we divided by. Okay, so on this one, I would take 360, and this one would take 5 turns to go all the way around. So I'm going to divide by 5. 5 goes into 36. Oops. 7 times 5 is 35. 10 would be 2, so 72 degrees, so we'd say yes. At 72, 144, okay, then add another 72, right? So 216, and then add another 72, so we get 288. And again, remember, we don't do 360, so we divide it by 5, we should have 1, 2, 3, 4 answers. All right, the sun. On this one, if we counted the number of rays, we could figure out how many turns it's going to take then. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 14, 15, 16. All right, so 360 divided by 16 is 4 would be, oh, this isn't going to come out nice, is it? All right, so 2 is 32, is 8, is 0, and 5 would be 30, so 8, right? So every 22.5 degrees. All right, and just for lack of quickness, we'll go ahead and put that in the calculator just to verify for one. Make sure I did my math right. 360 divided by 16 is 22.5. And then add 22.5, obviously that's going to be 45. Then add 22.5, 67.5, 90, 112.5, 135, 157.5, and remember we're going to go all the way up to 360, not including 360. So 180, I'm halfway there. Oh, and the last one would be 360. So we divided by 16, so we have 15 answers. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 14, 15. Okay? All right, now trick question. What happens if I do this? Now, does it have rotational symmetry? Well, no. Okay, because if I take my smiley face off here, if I spin it, it doesn't look the same until I go all the way around. Well, if it only has 360, okay, then we would say no. It does not have rotational symmetry. Okay? All right, our little three-sided jobber here, we got 360. We're going to divide by 3. So it's going to be 120. So we would say yes at 120 and 240. And again, we don't list 360. Okay, we got 1, 2, 3, 4, 5, 6, so we divide by 6. We've already done this. 360 divided by 6 gets me 60. So it would be yes at 60, 120, 180, 240, and 300. Okay, oh, this one's kind of neat. This is rotational. The word says rotational, but it also has rotational symmetry, because if I spin it, okay, it's the same. All right, if you want to, go ahead and spin your paper and you can see it yourself. All right, this one we would divide by 1, 2, 3, 4, 5. Let's see, we haven't had one work yet, but we'll give it a try here. Nope, not working. All right. We can also see this in nature. Okay, here we have our flower. We would have 1, 2, 3. I know it's not exactly perfect, but it's pretty close. So we would take 360 divided by 3. So it would take 3 turns. Okay, so 120. So I would say yes at 120 and 240. Okay, all right, now this is called polar graph paper. This is going to make what we did back here on the coordinate system, right here. I'm only ever going to have you do 90, 180, and 270 on this type of paper. Okay, but if I asked you to rotate it 30 degrees, okay, that would be close to impossible on this type of paper. So what we have is called polar graph paper. And the polar graph paper, you could do 30 degrees pretty easily. Okay, so if I said, let's say this is our original, okay, always count from the original, and let's say for A we want to go 30 degrees clockwise. Okay, so all I do is I count on each of the vertices in my shape. I'm going to go 10, 20, 30, and I went clockwise. Okay, 10, 20, 30, and 10, 20, 30. And we should end up with a triangle that's the same shape and size as our original, it's just turned. Okay, So let's do that again, and let's go, let's see what'll fit. Let's go 50 degrees counterclockwise. All right, so again, I'm going from my original. Okay, so this was letter A. All right, we're gonna do letter B. So we're gonna go 50 degrees counterclockwise. 10, 20, 30, 40, 50. 10, 20, 30, 40, 50. And 10, 20, 30, 40, 50. Okay, so again, I end up with the same triangle. It's just turned. All right, so on your piece of polar graph paper, I would like you to take this shape and let's go one of them at, let's go 60 degrees counterclockwise. All right, and then I would like you to go 80 degrees clockwise. And then I would like you to go 180 degrees. And again, I'm not going to say clockwise or counterclockwise on that one because it's not going to matter. Okay, either way. All right, give that a try and then call me over when you got it.